from UC San Diego. He's in the electrical and computer engineering department, and he's the head of the statistical visual computing lab. He got his PhD from MIT, and then worked at HP Cambridge Research Lab before joining UCSD. His research interests are in statistical signal processing, machine learning, and multimedia. So today we'll talk about understanding video crowded environments. Professor Vasconcelos.
First of all, thanks for the invitation to come. So I'm going to be talking about some work that we've been doing in understanding video crowded environments. Feel free to ask questions and stop me at any time. So this is work that I've been doing with my students, Anthony Chen, which is now graduating, Vijay Mahadevan and Wei-Shin Lin. It's sort of a new area that we're exploring. So maybe I should start by saying what we mean by crowds. So for the purposes of this talk, crowded scenes are scenes that are composed by many objects, typically, but they could also be particles. And those objects and particles are subject to complex dynamics. Now, one important property is these are scenes, or these are things that are perceived as a whole. And so some examples will be the types of crowds that I show here. A flock of birds, a school of fish, traffic on a highway, marathons, people running. So these would be like object type crowds. There could be like some, also particle type crowds, which are, you typically don't think of them in the same way, but perceptually they're not that different. And as you can see, the models that one can use to model, these types of crowds can also be used for these processes. And so the idea is that all of these things tend to be perceived as a single entity. So you don't think of these as like one fish and another fish, and then there's another fish in the back. But typically look at these and you say, oh, there's a school of fish, and that's about it. And that's how we perceive these type of stimulus. So we're interested in modeling and understanding how how does that happen, and how can we what can we do if we're able to model these processes. Okay, so a natural question that to ask is why what's the use of studying crowds or video crowds or crowded scenes, and there's a number of justifications for that. So the first one is, of course, that if we can understand these environments, we can find interesting applications of computer vision related to the solution of problems that are out there and need to be solved. And these involve the design of systems for traffic monitoring and crowd monitoring in general, and this could go from just your standard surveillance type of application, but it could also involve applications in, say, urban planning, where you're trying to figure out like how do you plan your streets so that the flows of the crowds are more natural, or traffic congestion, things like that. And then, of course, when it comes to particle crowds, there's a lot of interest. I come from San Diego. There's a lot of interest there in sort of preventing fires and things like that. So a number of applications there. So that's one reason is that there is a need for this type of modeling and understanding of this video, because the video is certainly out there. And there's nobody doing anything with it, just because it's it's too much video and there's little in the process of in the sense of automatically understanding it at this point. A second interesting reason to do this is that I work on computer vision, which is one of these phenomenally difficult problems where we've been working for computer vision for like half a century now, and there's we don't have a lot to show for it. And the reason is for that is that everything you do, you're always competing with this, massively optimized system, which is, the human brain or, whatever solutions biological vision has devised to solve this problem. And so it's always unsatisfying because everything you do, you can just, find somebody that is an illiterate and you could pay them like, half a cent an hour, and they would do a better job than your, a computer vision algorithm. And that makes it really hard to, make progress because we're always sort of, fighting against this standard, which is, near perfection. So that creates a problem. Unfortunately, that only attracts us towards more and more the problems that people are really good at solving. And less at the problems that people are not so good at solving. So here's an example of a problem that people are actually not very good at solving. This is a problem where I think we can actually build systems that actually solve problems better than people can. And I couldn't resist just giving an example of how poorly people can sort of solve crowd understanding problems. This is actually a story from the New York Times. So it turns out that there are many states have these rules where if you have a park or a public beach or something like that, you have to keep a log of how many people are using them. And so this actually is from the New York Times. It's in New York and related areas. And there was a piece that I thought was really interesting that showed how poorly we do these problems. That actually talked about how that problem is handled right now. And so I couldn't resist and sort of copy a little bit because I think it illustrates how we really don't have any solutions to deal with it. So the article goes, this is just a piece of it. It goes like this: twice a day, Mr. Ferrara, which is one of these guys that you see in this picture that come with the article, takes time out from his other duties as a city park supervisor to estimate how many people are on Coney Island's famous boardwalk and the adjacent 3-mile stretch of sand. Mr. Ferrara chose a few vantage points that afforded views of the most popular spots and made mental notes of how many people he thought they contained. He also surveyed the parade of arrivals snaking down the ramps from the subway station at Stillwell Avenue, using no tools or devices, not even a pencil and paper. Mr. Ferrara, 42, settled on an estimate of 120,000 people. He radioed into the Parks Department's outpost on the boardwalk, where Jackie Reagan, a seasonal guide, wrote in a black binder marked Beach Stats 2009. When Mrs. Reagan, 54, called the number into the department's offices in Lower Manhattan, it became, for better or flimsier, the official attendance for Coney Island's beach that day. Okay, and so and then there's they talk to the police department chief, and he talks about how hard it is to estimate crowd sizes and how they get into a hard time. Everybody does something at Central Park because people want to. There's all these conflicting reports about how many people attend, and so basically they stop doing that because it will only get them in trouble. So this is an example of a task for which we have really no there's no technology available. People can't really do it either. Okay, and so that presents an opportunity, say, for computer vision, where we could be doing things that would be successful by definition because there is no solution out there. So that's the second reason. A third reason is that modeling and studying these types of problems, it poses challenging new vision problems. And if you look at the history of computer vision, the fundamental trend that you would sort of identify is that it's based on the analysis of individual behavior for most part. And that individual behavior could be pixel level type of behavior, and we spent a lot of time doing things like computing optical flow and figuring out where what this pixel goes on the next frame and things like that. After that era, we went through sort of a lot of object level processing, which is sort of the dominant trend still today. So you would sort of identify objects, recognize them, track them in this video, so if you're trying to understand what's going on in a scene. And that turns out to be tremendously difficult. And it turns out to be tremendously difficult because, as the complexity of the scene increases, as you have more people or more cars or whatever, these objects start interacting with each other. They start, occluding each other. They're starting, what one object does depends on the other object. So, it's really hard to scale this type of process to sort of environments that are, more complex. Okay? And so it is a challenge. How can we sort of think about things that are 10 or 20 times more complex than these scenes that we can deal with, and where you really have densely packed crowds, for example. Okay, so it turns out that that type of approach, it's really complicated if you want to model scenes like this. Okay, and it's complicated not just because it's hard. So if you look at here, by the time you get to this part of the scene, each car has about like 4 pixels in it. So it's really hard to build a car model with 4 pixels. But it's also really hard because even if I could do this, even if I could track all these cars as they occlude each other, this guy goes over here and then gets behind the truck and I don't see it anymore and so forth. Even if I could do that, at the end of the day, what would I get? I would get, if there's maybe 1,000 cars here or whatever the number is, I would end up with 1,000 trajectories. And I haven't really simplified the problem at all, because now I have to understand, what are these trajectories about? How do I make sense of all these trajectories? So in some sense, I've solved a hard problem. But I created an even harder problem. And in fact, there's lots and lots of, we've been trying to do this for a long time, and there's lots and lots of, issues that come up. Trajectories get misaligned and broken, and then you have to, sometimes you have 2 trajectories and it's really the same object just because, there was an occlusion or something like that. They might have different lengths. Things might be moving faster on this side of the road than on that side of the road. So it's a really complicated problem. And even if you solve the really complex problem of figuring out what individually these objects are doing. What we've been working on is something that's different, which is, let's sort of ignore all of this, and let's really, deal with these processes in the way that they are perceived. If I asked you to sort of look at this video here, you would certainly not be tracking, cars individually. You would just say, oh, it's highway traffic and it's really congested, or it's not that congested, or whatever. But you probably wouldn't, go beyond that. It's not something that we can do, easily, as I just showed, in the previous slide. Okay, so we've been looking at the question of
what would you like to get?
Well, that's the question. Typically, you would like to get macroscopic properties. What is the flow like? What are the congestion levels? How should I reroute the traffic so that I balance the flows? So typically, you're interested in properties of the crowd itself.
So right now, people are using non-imaging sensors.
Right.
To give you the navigation system right in your car,
right.
Live traffic, where it is congested, where it is not. So people are getting their information from non-video sensors. Right.
You can get some of that information from non-video sensors. But that, for example, for cars, it's relatively easy to do because you can just put these wires on the pavement, and you can, even though they're extremely unreliable, nobody cares because you can't really do anything other than that. But you can't do that. For example, if you're asking the question, okay, I need, we need to do some construction here on campus. What areas do we block, and how do we reroute people or whatever? Then it becomes a lot harder because